Okay, chains. Many of the functions that chains are going to do is going to be similar to what we saw with belts. Okay. And the main thing that they have is that flexibility on center distance. But because of the fact that they have metal chains and links, and they're going to be pulling it around with what we call a sprocket now that has teeth on it, we say that it has more positive ability to transmit forces and motion, meaning we can use higher loads just because of the nature of the materials that we have, and that we have the teeth going up through there. Again, there's not going to be as much slippage as early. But some of the things that we liked about belts, chains don't have. So chains are going to be a little bit noisier. We're going to hear those. We're also going to have to lubricate them, which as a designer, that's going to be something else that we have to consider and design into wherever the application is going to be. But they are still considered a low-cost option. They're pretty cheap. They're quite available. I mean, we can go to Ace Hardware and we can pick up chain, right? So, so it is a nice cost-effective way of transmitting forces and motion. We are not going to have slippage because of the fact that those chains come up through, but what ends up happening then is we have jams, and then we can also have parts break along the way. Belts will just slip, you know, and that's kind of like by design again. More efficient at lower speeds than belts, meaning most often when they're lower speeds, there's usually higher forces that we're pushing through there, higher torques. So chains are going to be more suited for that. They don't require a lot of maintenance. Okay. And they do have a longer service life than belts just because they're made out of metal. Okay. So, so that's kind of like looking at kind of the differences. Now, there are going to be different types of chains here, and we're going to be looking at the most common. They can come in a multitude of different configurations, and there's a lot of different uses for chains. So I'm going to go over underneath. And on page 308, we're going to see the 4 most popular kinds of chains. So the first one here is going to be roller chain. Actually, the first 3 are roller chains, but just a little bit different configurations. So roller chain is going to have these side plates along the sides, and then they're going to have the pins going across with rollers over the top. The spaces that are in between here are where our sprockets are going to come up through. All right. Now, what's nice about roller chain, and they don't show it in this book, but you can literally take it apart. Okay. And then you can add things like pushers, and you can put them on conveyors, and they can actually time, for instance, moving packages or boxes or different parts into different locations. So they're used a lot in automation. Okay. You'll notice that we go from 1 strand to, in this case, 3 strands. We can actually gang together multiple strands together. And the advantage is we keep them at a lower profile on a sprocket, but we can then, you know, get the advantage of having, you know, more strength in that chain. The next one here is just an offset sidebar. So the sides are a little bit different rather than being straight plates. They're sides. There's like a little indent there, different configuration. And then lastly, this is called a silent type of a chain that we have here for it. The one that we're going to focus on for our examples is just going to be the standard roller chain. Now, chain pitch. Roller chain is going to be classified by the pitch that it has. So if we look at figure 11.9, up on the top of the following page, 308, we are going to see a side plate, okay? So as we look at that side plate, that's going to be what we saw earlier down here on the sides of the roller chain. Now, the distance between one pin and the other is going to be what we call the pitch, okay? Now, the pitch is going to be a distance, but when we talk about roller chain, we actually classify it in numbers, okay? So let's see if they have the numbers listed here. So we go on page 310. On the left-hand side here of table 11.5, you're going to notice that we have roller chain size, and it's all numbers, okay? And how this works is if you take a roller chain number 25, we're going to get the distance between those pins on that side plate in inches if we divide this number by 80. So take 25 and divide it by 80. What do you get? 0.3125. So that's 5/16, right? So if we go back over here, the distance between those two pins is 0.3125. Okay, let's do it for another one. Let's do it for number 40 chain. If we take 40 divided by 80, what do we get? 0.5, right? So if we take 0.5, that's the distance between those 2 points. Now, if we look back down here, then that's going to be the distance from one roller to the next, to the next, to the next. Okay, so the number corresponds to the pitch. When we divide that number by 80, it's the actual, distance or the dimension in inches. Okay, so good. Now, as we look back at that, I'm just going to kind of point something out before we go too far. As we look at these numbers, if there is a roller chain manufacturer out there, they are making these standard numbers, and those also correspond. And this is when we're in design of machine elements, we're going to be doing this again, but we're going to be finishing up the design, if you would, by sizing it now at that time, or then, or coming soon in the future. We're going to be adding in the strength then of the actual chain, and if it's going to be appropriate for the application that we need. Right now, again, we're just worried about rotational speed and our physical size. Okay, but in machine design or machine elements, we're going to be looking at now how much strength can that pull. So as this chain gets larger, what do you imagine happens to the tensile strength of that chain? It's going to go up, right? Yeah, that would make sense. So what we're going to be doing then is we'll be comparing sizing of that chain based on the larger the chain, the more that it can take. All right. Larger is going to have greater power capabilities. Multiple strand chains. So we saw the multiple strand chains that we had there. They will increase the amount of power that we can transmit through that chain drive, but they do not provide a direct multiple, meaning if there's two chains, it doesn't double the strength. Okay. If we look on page 310, we have the factors up on the top on table 11.4. So up here on table 11.4, if we have two chains, the strength factor is only 1.7. We have three chains, it's 2.5. So again, just because we have extra chains there doesn't mean we get 2 times, 3 times, and so on. This is going to be the actual factor. Why do you think that is? Why do you think that is? Why aren't we getting direct multiples?
Like you're using some of the same side plates.
Yeah, we're sharing some side plates in those inside ones, so we aren't getting like the doubling or the thickening, on each one of those plates. Right, exactly. So so just keep that in mind, that even if we're ganging them up and we're putting more together, we will get more out of it, but not to the true factor of how many strands that we multiplied by. Okay, so those are there for you. All right, sprockets. Okay, so sprockets are going to be the drivers of those chains. Sprockets are going to have teeth on them that are going to fit up into those spaces of the roller chain. Okay, and we all should be familiar with that based on our experiences with riding a bike and such. So the teeth are designed with geometry that's going to conform to that chain. So just like we had for gears, just like we had for V-belts, if we have a certain size sprocket tooth, we have to then match it up with the right chain that's going to fit with it. So if we have a number 80 chain, that means we have to have a number 80 sprocket as well. Okay, just like with teeth, we had to have the same diametral pitch on the teeth so that they would mesh together. For the V-belt, we had to have the V-belt that would fit into the groove on our shiv. Now we have sprockets that have to fit with their appropriate chain sizes. Okay, so if we look at 11.1, this is going to be a sprocket. Okay, so in this sprocket, you'll notice that they have teeth going around. Now they don't look exactly like gear teeth, but they're kind of like gear teeth. And then those roller chains are going to fit over the top here. And then the sprocket is going to pull those chains along. Now, as we look here, this is going to be the, you know, what the drive looks like. So on the left-hand side here, we're going to assume that this is going to be our faster moving sprocket. So this is going to be our driver. So you're going to notice the W1 consistent with what we did earlier with our V belt. And then W2 is over here, or pitch diameter 2 is over here as well. The pitch diameter for a sprocket is going to be about, not exactly, but in the middle of the tooth there again. It's that effective diameter where the forces are actually being concentrated and pulling that chain along for it. So if this is going in a counterclockwise direction, the tight side is going to be on the top. If it's going counterclock or clockwise direction, then the tight side will be on the bottom. Okay, yes. The most often it's going to be on the slack side. Exactly. Yeah. Because that way chains over time will also have that same pulling effect and they're going to sag over time. So, so the tensioner will usually go on that side because that'll take up the amount. And then you have to, again, build in what you're going to be doing. Sometimes the tensioner can be this way. You can also have it on the one of the sprockets, but a lot of times you're going to have it, you know, separate on the slack side. Yeah. Good question. Anything else? Right. So it all kind of looks familiar. Notice this VC, this is now going to be the pitch line speed of the chain. Okay. And it's going to have that same equation we're going to find out that we had for belts and for gears. All right. Chain drive geometry. Ooh. We're going to look at, we looked at figure 11-12. And then we're going to look at the equations on the next page. So over on the left-hand side, we're going to notice that we start out here. We have our pitch diameter. Okay. Our pitch diameter is going to be calculated using the pitch on the top. Now, this pitch is going to be in inches. Okay. That pitch is going to be in inches. And then the N is going to be the number of teeth. Okay. It's going to be the number of teeth. Yeah. Okay. I was going to say units aren't coming out quite right, but it's because of the sign here. So inches on top. So we're going to be ending up with inches. Then you're going to notice that we're going to determine our center distance by it being within this range again. So we're going to take the pitch in inches. So this pitch capital or this small p is going to be in inches. And that one's going to be in inches. So we're not going to put the number pitch in there. So for instance, if it's an 80 pitch chain, the pitch is actually 1 inch. Okay. We're not going to put 80 in there. We're going to put the equivalent in inches. So this would mean that if it's 1 inch pitch, this would be, the center distance would be between 30 and 50 pitches. Okay. 30 and 50 inches, not pitches. Okay. Now, once we kind of determine that chain length, then we need to figure out, now this is something that's different, but it's got the same variable. So when we're dealing with chains and we want to figure out the length of a chain, in this case, we're going to be counting links. Okay. And a link is going to be each one of these separate spaces. Okay. Link, 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 link. So we want to know how many links are we going to need to wrap around our driven and our driver sprocket and maintain the center distance that we want. Okay. Now go ahead.
So that's what
Capital L for chains is links. This is going to be links. Okay. In belts, it was length. So same variable, but because it's chains, it's going to be links. So now we're going to find out how many links do I want to pull off the roll of chain that I have. Okay. So many times in industrial setting, if you're getting chain in, you get it in bulk, and then you just count the number of chains. So we'll estimate our center distance. We're going to use that estimated center distance to determine how many links are we going to need to get right about there. And then once we get our links, we're then going to take that number and we're going to round it up to the nearest even integer, because we can only have even integers of links, okay? And then once we know exactly how many links we're using, then we're going to plug it back into this equation for the actual center distance. So kind of like that iteration type of a process that we did for belts as well. I know, here we go. Do you want me to, can I get it closer for you? Here it is. Do you need it? I know, it's a long one, but that's okay. Long is good. Don't you feel smart when you go home and your, you know, your family, your friends ask you, hey, what did you do today? What did you learn today? Don't you feel like, well, let me tell you.
So which, because in the book they had pitch was the diameter. So
oh, no, this is not pitch diameter. This is pitch for
chain.
Exactly, your chain length. So remember when we talk about, you're right. This is, you know, I don't think of it all the time, but this is pitch diameter. This is going to be the distance across the sprockets on the effective diameter, if you would. That's pitch diameter. That's the physical diameter on the actual sprocket. Yes, the little p, great way to say that, is the size of the link, little p. And then D1, D2 is pitch diameter. Yeah. And we'll do I think one or two examples here to kind of practice all this stuff.
And you said N is the
number of teeth. Yep. So that's consistent with gears. Gears were N's were numbers of teeth as well. And the fun thing about this is, even if it seems a little blurry right now in kinematics when we're learning this stuff, we'll get to do it again in machine elements. And then it'll be like, oh, second time you're hearing this stuff. And then it makes a little bit more sense. It sinks in a little bit deeper. Did you ever notice that? First time you kind of learn something, it's like, well, kind of get it. Second and third time, you're like, all right, now I got it. And then like by the 80th time and the 800th time you've done Pythagorean's theorem, you're like, yeah, all right, it's enough. All right. And then the very last two equations here then are going to be those wraps. Okay. So we want to know how much wrap, what angle of contact do we get on each one of our sprockets. And again, we want it to be at least 120 degrees. Okay. So theta 2 is going to correspond to the driver. Theta 1 is going to correspond to the driven. Okay.
Why is that not the same or like belt? Because of,
well, they're using number of teeth here instead of pitch diameter. They're using the number of teeth instead. And then on the next column here, we're going to be our familiar favorites. Velocity ratio. Now here we're adding teeth back in again because sprockets have teeth on them. So we can count teeth again on a sprocket, just like we were able to on a gear. All right. And then we have the pitch line velocity of our chain this time. And now this is going to be that radius. So that's D1 divided by 2, which would be radius 1, times your angular velocity. And remember, these have to be in radians per second. Okay. Or radians per minute, I think they use, so that they leave it then in like feet per minute as their final units. Okay. Whichever one. Okay. Now, the very last consideration that we have, and they mention it here, but we'll be looking at it more closely in the example, is that we have lubrication that we have to consider. So once we know how fast our chain is going, if we're a low speed, a moderate, or a high. So low speed is going to be anything that is going to be less than 650 feet per minute. And then we don't have to have any lubrication at all. Okay, maybe periodically adding a little bit, kind of like on your bicycle, right? Every so often, but it doesn't have to be on a regular basis. Just when it feels like it needs it. When you've got moderate, which is anything 650 to 1500, then we need to have a bath lubrication, okay, where the lowest point on the chain goes down in and kind of brings it up. And then when we have higher speeds than 1500 feet per minute, then we want to actually have an oil stream that's like on the chain, you know, all the time. Okay, so depending on where you're at, you as the designer may have to build in some actual lubrication if needed. Okay. All right. So I think we should be ready to start looking at our next example. Okay. So let's read the example first. Actually, oh, this is the last example we'll be doing actually. So, so we get one. So we'll look at the problem itself. And here we're going to be identifying a single strand roller chain drive. It connects to a 10 horsepower engine to a lawn waste chipper shredder as shown. So on the following page here is the drive. So we're here with our W1 and here with our W2. Okay. As the engine operates at 1200 RPM, the shredding teeth should rotate at 240 RPM. Okay, so this is our W2, right? And this is our W1. The drive sprocket has 18 teeth. All right, so that's N1. Determine the appropriate pitch of the chain. Okay, so that's going to be our P, right? The number of teeth in the driven sprocket, so we need N2. The pitch diameters of both. Okay, so that's going to be a D1 and a D2. And the chain speed. So that's going to be a VC this time. Also indicate the number of links, L, for a suitable chain, and specify the required center distance. Okay, so that's going to be C. So we got a whole bunch of stuff to do here. Last time I think we just had 4 things. Now there's like a lot. So as we look here, center distance wise, again, they're not giving us one. So we're going to have to use that range and pick one, right? Okay. So as we look at our problem, the first thing we're going to do is we're going to determine what is the pitch size that we need. Okay. So to do that, we're going to look at figure 1110. Okay, figure 1110. So down here on page 309, you're going to notice that we have this chart. Okay. I know hopefully those who are virtual, you have your book handy and you can kind of read this because it's not going to be easy to come through. So this is your chain pitch selection guide. On the bottom, this is going to be the speed of the small sprocket in RPMs. Okay. And I'm going to try to zoom in here because the numbers are pretty small. So we started at about 10 and we're going to go up. And you're going to notice that it goes up to about 10,000. Okay. So if I remember, what was ours? 1200. 1200 RPM is going to be on that faster one. So we're going to find 1200 is right here. Okay. And then we want to find, as we look at the top of our Y axis, these are the numbers of strands, and we are in a single strand. So we're going to use this column going down closest, and the horsepower was 10. Sorry, 10. So we're going to go down to 10. So 10 is here and 1200 is here. Okay. So we're right in kind of the edge of the 40. So I would say you could go 40 or 50. Do you see that? You could really go 40 or 50. I'm going to see what they chose. Did they choose 40? Of course they did. Of course they did. We'll go with 40 because that's what they chose. That's fine. So they chose the 40 pitch and they're not wrong. They're not wrong. But I will tell you, when we're in machine elements, there's going to be that design horsepower and there's going to be some factors that we're going to multiply in that's going to bump that up a little bit, and it probably would push it up into the next size, but that's okay. We're gonna go with the 40 like they said, okay? Only because at the kinematic level, we aren't worried about the forces. We're just looking at movement. So that's why, yeah. So I just want to let you know later on, you might be like, why are we doing this now? It's because then we're gonna have, and we do know the application. I'm not sure why they don't put it in here because we know that it's a chipper, which is kind of volatile. There's going to be a chance for probably more jams than anything else. So you want to kind of put the design horsepower up a little bit so that, you know, you can accommodate some of that. So I'm not sure why the book doesn't do it. And yeah.
Well, maybe it only on the 5 and stuff like that.
You might be right. They don't tell us that. They're saying, I think they tell us that the engine itself is a 10 horsepower. So maybe you're right. Maybe they're already bumping it up. Let's hope so, right? Let's hope so. So we'll just go with that, but there's going to be a little bit more in that identification when we're taking into consideration more 4C types of things. Okay. So now that we know what the pitch is, now we're going to determine what the number of teeth are on our driver and our driven. And we're going to use that same process that we did when we were looking at it for our belts. So I'm going to start my example here. And we already know that this is number 1. We're going to be using the number 40 chain. Okay, so that's going to be our pitch. And our pitch then, P is going to be the number of the chain divided by 80. So our pitch is going to be 40 divided by 80 or 0.5, and that's going to be inches. Okay, so that's going to be our P for the chain that we've chosen. So our step number 2 now is going to be picking the sprockets. So we know that our velocity ratio is W1 divided by W2, and we can set that equal to the number of teeth on our driver divided by the number of, the driven, number 2, divided by the number of teeth on our driver. That's that same equation that we were using earlier. So now for this problem, we need to pick the number of teeth here, knowing that our W1 is going to be 1200 RPM, and we are trying to achieve as close as possible to, is it 240? Yep, 240 RPMs. Okay. So we need to pick these two numbers. So we're going to do that very same thing that we did last time. We're going to take N1, we're going to multiply it up, and we're going to multiply it by whatever our velocity ratio is. So our N1 times, and if we take the 1200 and we divide that by 240, it's 5. Did you guys get that? Yeah, that makes sense. So it's going to be 5 is equal to N2. So this is where we start trying out pairs. Okay. And instead of taking all the time to try out 3 and 4 pairs, why don't we look at what they chose in the book? Okay. Because you kind of get the idea, right? How you would approach this. So, so when they did this, it looks like they came up with 18 and 90, right? So if we look at the list of commercially available single strand sprockets, okay, and we go to the number 40, you're going to notice that they're going to be available in the number of teeth starting with 8 and in every single number through 60. And then after 60, it's going to go to 64, 65, and so on. All right. So they chose what? They chose 18, and then multiplying that times 5, you check, is there a 90? There is. Okay. And that's how you would go about this. All right. So, so they picked N1 equal to, did you say 18, right? No. And then our N2 is equal to 90. All right. So these are going to be the number of teeth on each one of our sprockets. Okay. Now we also need to know, as I look at my problem statement here, I need to know what is my D1 and my D2. Okay. So if I go back up to the top of page 311, here is the equation for the pitch diameter. So we want to figure out P1 or D1 and D2. So using those values, our step number 3 here then is going to be D is equal to, and it's going to be the pitch in inches divided by the sine of 180 divided by the number of teeth. Okay. So if we're doing D1, that's going to be the number of teeth on that first sprocket. So our pitch here is going to be 0.5 inches divided by the sine of 180 divided by 18 teeth, right? So now our D1 is going to equal. So it should be 2.879 inches. Is that what you got? Yep. Okay, cool. And then we're gonna do the same thing for D2. So this is one of our answers. Our D2 is going to be our P divided by sine of 1. I'm going to just write it here because our equation is up there. It's going to be 0.5. Same pitch, inches. 180 divided by 90 teeth, right? Parentheses around the right thing. So D2 ooh, that's not right. You get 16.67? No. What did they get? My numbers are right, correct? Yeah. Okay, so that's our second diameter, okay? Now, the next thing we need to do is, well, let's look. We've got our number of teeth and 2 and 1. We've got D1, D2. We picked our pitch. We need to find center distance, right? And the number of links, right? Okay. So center distance, we are going to pick based on the range that we have here. So step number 4 is going to be 30 times our pitch. Going to be, our center distance has to be greater than, and it has to be less than 50 times our pitch. So if that's the case, our pitch is 1/2 inch, right? So our pitch is 0.5 inches for both of these. So we're going to be between 15 inches and 25 inches. I did that correctly, right? So in the room, who wants to pick our center distance? 20, again. Is that what the book shows? I don't know. It is in the middle. Is that what we want to do? Sticking with 20? They chose 22. Okay. 20 as well. Yes. Okay. So we're going to do 20 inches, and that's going to be our trial, right? That's going to be our trial center distance. Okay. So now with our trial center distance, we need to calculate the number of links that we're going to use. So this is kind of like a big equation. I'll zoom in here so that you have it in its variable form. So our step number 5 now is going to be our trial number of links. Okay. So 2 times C divided by P, that's our pitch in inches, plus N2 plus N1 divided by 2, plus our pitch times N2 minus N1 squared, 4 pi squared divided by C. There we go. And it's a good idea to practice putting these in, because I realize now I don't use like a programmable calculator. I kind of do mine step by step, but and it's a personal preference, but make sure that you can get the numbers in here so that you get the same answers. That's why doing these example problems is kind of nice, because then you know that how you put it into your calculator was correct, because it can be just one little, you know, wrong sign or a wrong button, and it can set everything off. So did you get 144.3? Is that the number in the book too?
Yes.
Worse. Where am I on? I have all the right numbers. Center distance. Lengths. Wait. Oh, I didn't square the pi. That's why I didn't square the pi. So 137.28 lengths. Did you guys, those who are online, did you guys get the same thing? Okay. Yeah, when I looked at the equation, I did not square the pi. That's my difference. Otherwise, my numbers were all the same. Easy to forget, easy to forget. So 137.28 links. Now, the 0.28 we can't get off, right? It has to be an even number. And the suggestion is that it's I'm sorry, it's an integer number and it has to be, you know, if at all possible, an even number. That's going to be the first preference. So you'll notice that they went up to 138 links. So what that means is off of that spool of bulk chain, we literally count link until we get to 138. So our actual number of links then, links actual is going to be 138. Okay. Okay. I know, it's like, oh my God. Oh, shocker.
So you always round it up.
We round up to the next integer, the whole number, but also it's also suggested that they be even numbers.
All right, okay, that would make sense,
Yeah.
because I mean, 18 and 92.
Mhm. Yep. All right, so then step number 6, now that we have these, now we want to calculate the actual center distance, So that's going to be this really long equation. Okay, so now you're gonna put in your L here, the 138, and then you're gonna use your number of teeth. The L is gonna be the 138 again. Make sure you pay attention to the squares. That's what I forgot. And you should get a center distance of 20.187. Okay, so take time to plug this in, making sure that you're getting the correct number. I'll leave this up here. So in case you need to reference it, I'll kind of pull it in here. Okay, not a bad idea to write it out. Well, I'm not gonna rewrite it. I'm gonna use theirs in the book here and just make sure I can get their very same number.
Yeah.
Yes, I got it. I got it. Yep, so that's a good number. Those are good numbers there. And you should get the 20.187. Yeah. Yeah, so make sure you've got the right brackets and the squares and all that kind of stuff, because I know it can get pretty complex when you're putting it into a calculator all in one. Are you guys able to get it all in one, or do you do it in stages?
I can do it all in one month.
You are fancy.
Actually, he's looking on mine. The one that's on the battery doesn't work unless they.
Oh,
bright
it's a
light.
solar, yeah. I do it the old fashioned way. I kind of do it in chunks and then together, so. All right. So there you have it. I think, oh wait, I think we have to do belt speed yet, don't we?
Yeah, we have one.
We have belt speed to do. Belt speed to do. All right, step number 7. We didn't do it in the order that the book did. So the last part that we need to do is going to be not our belt speed, our chain speed, which is going to be our D1 divided by 2. This is our radius times our W1. Okay, and remember, this has to be in, and we're going to put it this time like they did last time in radians per minute, because we're going to put our chain speed in feet per minute. Okay, so go ahead and calculate your chain speed, the pitch line chain speed this time. So our D1, our D1 was 2.88 inches divided by 2. And then we're going to have, this is our W. So we know that to be 1200, right? 1200 RPMs. Yep. Per minute. 1 revolution. 2 pi radians. Oh, I was going to leave it in radians per minute. That's right. I don't need to divide by 60. So 7,539.6. We'll leave it in radians per minute. Okay. So this is going to be 7,539.6 radians per minute. There we go. Okay. And that goes there. So our chain speed is going to be 21,000. I'm going to put that down here a little bit because we'll do one more conversion. Our chain speed is going to be 21,714.1 inches per minute. Inches per minute. And then now we just need to divide by 12 to get it into feet per minute. So our VC 21,714.1 12 divide. 1,800 9.5. I'm gonna put FCM. I don't know. I'm thinking I'm kind of high.
Oh.
Oh, let me see. So 1,200 2 times 3.1415 times 7,000. That. Oh, you know what I didn't do? I didn't divide by, I just multiplied by 2.88. I'm sorry. Dang it. What was that? Oh, no. What was that? Don't, I'm sorry.
No, it's a running joke now. It's.
I know, I'm sorry. It really, yeah. There we go. 904, 905. 904.7. Yeah, that looks like it's a good number. And actually, in their problem in the book, I did correct it because they have the wrong. They have 10,838 for their radians per minute. It should be the 7539.6. And then you end up with the 904 here for your problem. Is that corrected in your book? No, yeah. Yeah, so if you are following along in your example, they have the wrong radians per minute. It should be 7539.6. Oh, sure. Yeah. They mustn't have done that problem. All right. So what was that?
I plug mine in, I'm just getting 10,800. So
For,
W. Like 1,200, right now, 2.88 times 1,200.
oh, for this one?
Yeah.
So,
Yeah, I'm getting 10,857.
yeah, that's what I got too.
Okay.
Yeah, their number isn't correct. I have that crossed off here. Yeah. So that should be 10,857. You're correct. And then this isn't correct. And then you should end up with 904 feet per minute. Yeah. Okay. Any questions at all? Did that make sense? Here, look at this. This one's better. It's 904.7 is what I ended up getting, 7.5. Okay. All right, so that takes us to the end of the chain stuff. So now let's go back to our PowerPoint. You're going to notice that you are now ready to begin the assigned homework problems related to chains and belt drives. So we already looked at the belt drives as far as the assignment. Let's take a peek at the chains assignment so you're kind of prepared and can kind of line them up with some of the things that we've done this evening. So I'm going to go back to the end of our chapter. And as far as chain problems, on page 314, down, starting on 1118, this is gear or chain kinematics. So you want to, with the description here, I'm not going to read it all to you. You want to determine the speed of the driven sprocket. So that's going to be a W2, the chain speed, that's going to be a VC, and the recommended lubrication method. So once you get your VC and you have it in feet per minute, you're going to compare it to either a slow, moderate, or high speed application and which lubrication would be appropriate for that. Okay. Number 20, it looks like you want to determine the speed of the drive sprocket this time. So that's going to be a W1. The chain speed, that's going to be a VC, and then also the lubrication method again. Okay. So they're giving you, oh, wait. Oh, the speed of the drive sprocket. Yeah. So you have to figure out how many RPMs that has to go to get the 250 on the output. Okay. Then our next one up here, you want to determine the pitch diameter of each one of the sprockets. In the description here, you've got a number 80 chain. Their center distance, C, the angle of contact, that's going to be the theta 1 and theta 2. Oh, it just says over the smaller sprocket. Sorry, just theta 1 then. And also compare the center distance that you end up with here to see if it falls within the ideal range. Make sure you answer that, okay? Just don't be like, center distance is this, but then say it's okay or not, right? And then the last problem that you have is going to be just like the full example that we just looked at. And here you're going to select the appropriate chain size, commercially available sprockets, the number of links on the chain, the actual center distance, and the chain speed. Okay. Oopsie. So that's exactly like the problem.
Run into a situation where we're right with the focus.
Oh, in the back of the book, you mean?
Yeah.
Well, remember, especially when we're looking here, there's going to be multiple pairs that come up as far as what's available. I don't know that they specify any of the actual sprocket sizes. What I think they do is give you maybe some intermediate information along the way. For instance, chain size. Okay. And that way you kind of know, okay, I'm on the right track with the chain size. Well, again, it comes down to what do you pick for your sprockets? And I would have to have like
Unfortunately,
a bunch of them.
check out, but then.
I look at your process and then are the numbers reasonable? So I know when I look, and then I'm looking for, formatting, making sure that, you're writing out the equation in variable form, you're putting your units in, you're, all that kind of stuff. And then I can make sense of the process. And if it's going along, then I compare back to is your center distance within, what your values would have been. So yeah, it takes a little bit longer for me to correct them, but that's okay. That's okay. Other questions? All right, so that is all that I have for module number 6. Let's just peek back at our assignment number 6, which is down here, and the problems that we just looked at. The first half, if you would, are going to be our V-belt, and then the last half is going to be the chain drives. Make sure this is all written work, that you do it neatly, that I can read it, that you show your equations in variable form, really kind of follow how we've been working them and how I've been kind of showing them here. If you end up kind of going in different locations, try to number your steps then for me. If you're not, moving down the page in a linear fashion, that's okay if you don't, just kind of tell me where you're going. Okay. And that's it. Make sure you put a box around your final answer, include your units, the variable, that kind of thing. Make sure you're answering and all the things that they're asking for as well, because a lot of these are multiple parts. Okay, so then I'm going to stop the recording here for chains, and then you can let me know if you have any questions.